welcome to this problem walkthrough. Today, we'll be exploring problem number 814, binary tree pruning. This involves working with binary trees and implementing a pruning strategy based on specific conditions. Let's dive in and break it down step by step. In this problem, we are tasked with pruning a binary tree based on a specific condition. The condition is that any subtree that does not contain the value 1 must be removed. A subtree, in this context, includes a node and all of its descendants. For the input, you're given the root of a binary tree where each node has a value of either 0 or 1. The output is the same binary tree, but with all subtrees that fail to meet the condition removed. This means we'll traverse the tree and recursively eliminate any subtrees that do not include a 1. Before diving into examples, it's important to keep in mind that the pruning process modifies the tree in place, so our result will be the pruned version of the input tree. Let's look at the first example. The input tree is represented as 1, null, 0, 0, 1. When visualized, the tree looks like this. There's a root node with the value 1, which has a right child with the value 0. That right child has two further children, a left child with the value 0 and a right child with the value 1. After pruning, the output tree is 1, null, 0, null, 1. When visualized, the pruned tree retains the root node 1, the right child 0, and the right child's right descendant 1. The left child of the right node, which had the value 0, is removed because it does not contain the value 1. To elaborate further, in example 1, we remove the leftmost leaf node with value 0 because it doesn't contain or lead to a 1. On the other hand, the subtree rooted at the second 0 is partially retained because its right child contains the value 1. Now, let's examine another example. Here, the input tree is 1, 0, 1, 0, 0, 0, 1. When visualized, the root node 1 has two children, a left child 0 and a right child 1. The left child has two children, both 0, while the right child has two children, a left child 0 and a right child 1. This tree is more complex, so pruning will involve evaluating each subtree carefully. The output for this example is 1, null, 1, null, 1. After pruning, the tree retains only the nodes that either contain a 1 or lead to a subtree containing 1. In the visualized pruned tree, we see that the root node 1 is preserved, and so is its right child 1, along with that right child's right descendant 1. All other subtrees rooted at nodes with the value 0 were removed because they do not contain the value 1. This includes the entire left subtree of the root and the left subtree of the right child. Essentially, any part of the tree that doesn't satisfy the condition of containing at least one 1 is eliminated. In the third example, the input tree is 1, 1, 0, 1, 1, 0, 1, 0. When visualized, the tree has a root node 1 with two children, a left child 1 and a right child 0. The left child itself has two children, both 1, and one of those children has a left child 0. The right child 0 has a single right child 1. This tree is larger and has more branches, which means the pruning process will involve recursively evaluating each node and its descendants to determine whether they should be removed or retained. After pruning, the output tree becomes 1, 1, 0, 1, 1, null, 1. When visualized, the pruned tree keeps the root node 1, its left child 1, and the right child 0. For the left subtree, both children of the left child 1 are retained, as they contain the value 1. However, the leftmost leaf node with value 0 is removed because it doesn't contain a 1. On the right side, the right child 0 is preserved because it has a right descendant containing the value 1. In this way, the pruning process ensures that only nodes that directly or indirectly contain the value 1 remain in the tree. There are a few important constraints and edge cases to consider for this problem. First, the number of nodes in the tree is guaranteed to be between 1 and 200, so we are working with relatively small trees. Additionally, the value of each node is either 0 or 1. For edge cases, consider a single node tree. If the node's value is 0, the entire tree is pruned, resulting in an empty tree. If the node's value is 1, the tree remains unchanged. If all nodes in the tree have the value 0, the output will always be an empty tree. Conversely, if all nodes are 1, no pruning is needed, and the tree remains as is. For more complex mixed trees, each subtree must be evaluated carefully to determine if it contains at least one 1. any subtree without a 1 will be pruned completely. To solve the binary tree pruning problem, we first considered two main approaches. The brute force approach is straightforward but inefficient. Here, the idea is to traverse the tree and, for each subtree, count the number of ones it contains. If a subtree has no ones, we prune it by removing its reference. However, this method is computationally expensive because it requires a separate traversal to count ones for every node, followed by another traversal to prune the subtrees. This redundancy leads to a time complexity of O(n squared, where n is the total number of nodes. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. The main drawback is that this approach involves multiple passes over the same nodes, which makes it highly inefficient. To address these issues, we turn to an optimized recursive approach. This method leverages post-order traversal, where we process the left and right subtrees first before making decisions about the current node. By pruning subtrees during the traversal itself, we reduce redundant checks and complete the task in a single pass. The time complexity here is O(n), as each node is visited only once, and the space complexity remains O(h), matching the height of the tree. This method is both efficient and elegant, making it a much better choice for this problem. The optimized recursive approach was chosen because it meets the problem's requirements in the most efficient way possible. By using post-order traversal, we ensure that each node is processed after its subtrees, which naturally aligns with the pruning criteria. The key insight here is that the decision to prune a node depends entirely on the state of its children and its own value, which is why post-order traversal is such a perfect fit. This approach avoids redundant checks and ensures that each node is handled only once, leading to an optimal solution. While the brute force approach might seem simpler conceptually, its inefficiency due to multiple traversals makes it unsuitable for larger trees. On the other hand, the optimized recursive method achieves linear time complexity, which is the best we can achieve for this problem. We also note some key observations. First, post-order traversal is a natural way to approach the problem. Second, the recursive nature of pruning decisions ensures that each node is evaluated in the context of its children. And finally, this approach is both time-efficient and space-efficient, making it the most practical choice. The final complexity analysis reveals why the optimized recursive approach is the ideal solution. The time complexity is O(n), where n is the total number of nodes, because each node is visited exactly once during the traversal. The space complexity is O(h), where h is the height of the tree. This accounts for the space used by the recursive call stack, which is proportional to the depth of the tree. Iterative approaches were deliberately avoided because they would require manually managing a stack, which would increase the implementation complexity without offering any substantial gains in efficiency. Recursive post-order traversal, on the other hand, provides a clean and intuitive way to solve the problem while achieving optimal performance. This balance of simplicity and efficiency makes the optimized recursive approach the best strategy for this task. To solve the binary tree pruning problem, we need to modify the given tree so that any subtree containing only zeros is removed, while subtrees with at least one node valued at 1 remain intact. This means our task is to traverse the tree and identify subtrees that can be pruned. The approach best suited for this is post-order traversal, where we process the left and right children before considering the parent node. This traversal ensures that we evaluate and make pruning decisions starting from the leaf nodes and moving upward. By using this bottom-up approach, we ensure that the tree structure is preserved correctly while removing unnecessary subtrees. To implement this, we define a helper function called contains1 that checks if a subtree rooted at a given node contains a 1. If the node is null, the function simply returns false, as an empty subtree does not contain any ones. For non-null nodes, we recursively call contains1 on the left and right children. If the left subtree does not contain a 1, we prune it by setting the left child to null, and similarly for the right child. Finally, the function checks the value of the current node and its subtrees. If any of these contain a 1, it returns true. Otherwise, it returns false. This way, the function ensures that only the necessary parts of the tree are retained. After defining the helper function, we call it on the root of the tree. If the root itself does not contain a 1 and all its subtrees are pruned, we return null. Otherwise, we return the modified root. Post-order traversal is critical here because it allows us to process a node's children before deciding whether the node itself should be pruned. This ensures that the pruning decisions are correct and do not disrupt the tree structure. The recursive nature of the algorithm simplifies the traversal and pruning process, as it allows us to backtrack and make pruning decisions as we return from deeper levels of the tree. Edge cases must also be considered. For example, if the input tree is empty, we return null immediately. In the case of a single node tree, we return the tree if the node's value is 1, otherwise, we return null. For larger trees, the algorithm efficiently processes all nodes with a time complexity of O(n), where n is the number of nodes in the tree, and a space complexity of O(h), where h is the height of the tree, due to the recursive call stack. The pruning process itself is straightforward. Whenever a subtree does not contain a 1, it is pruned by setting the corresponding child reference to null. For instance, if the left subtree of a node does not contain a 1, we assign null to the node's left child. The same logic applies to the right subtree. The evaluation of each node centers around the contains 1 function, which checks whether the current node's value is 1 or if any of its subtrees contain a 1. This function ensures that only nodes in subtrees with at least one node valued at 1 are preserved. The time complexity of the algorithm is O(n), because each node is visited exactly once, and the space complexity is O(h), where h is the height of the tree, due to the recursive function call stack used during traversal. Here is the pseudocode for the pruning process. We define a helper function contains 1 that performs the recursive traversal. If the current node is null, the function returns false. It then checks the left and right subtrees by recursively calling contains 1. If the left subtree does not contain a 1, the left child of the current node is set to null. Similarly, if the right subtree does not contain a 1, the right child is set to null. Finally, the function returns true if the current node's value is 1 or if any of its subtrees contain a 1. The pruning process is complete when contains 1 has been applied to every node, starting from the root. If the root itself does not contain a 1 and all its subtrees are pruned, the entire tree is set to null. Otherwise, the pruned tree is returned. For example, consider the input tree where the root has a value of 1, with a left child containing a mix of zeros and ones and a right child containing only zeros. Starting at the root, we first recurse into the left child, which has a value of 0. Its left subtree contains only zeros, so it is pruned. The right subtree contains a 1, so it is retained. As a result, the left child of the root is preserved, but with its left subtree removed. Next, we recurse into the right child of the root, which contains only zeros. Since this subtree does not contain any ones, it is pruned entirely. Finally, the root is evaluated. Since its value is 1 and it has a valid left subtree, the root is preserved. The resulting pruned tree has the root with a left child, which in turn has a right child. This illustrates how the algorithm effectively eliminates unnecessary subtrees while retaining the essential structure containing ones. Here, we start by defining a tree node class, which is the basic structure of our binary tree. Each node has a value, as well as optional left and right child nodes. We then define the solution class, which contains the prune tree method to solve the problem. Inside this method, there's a recursive helper function called contains1. This function is designed to traverse the tree and determine whether any subtree contains the value 1. If the current node is null, the function returns false, indicating that there is no one in this branch. Next, it recursively checks the left and right subtrees to see if they contain the value 1. After evaluating the left and right subtrees, the function prunes them by setting the corresponding child to none if the subtree does not contain a 1. Finally, the function returns true if the current node's value is 1 or if any of its subtrees contain 1. This ensures that we only keep the relevant parts of the tree. The last step in the prune tree method is to call the contains1 helper function on the root node. If the root itself, along with its subtrees, does not contain a 1, the entire tree is pruned, and we return none. Otherwise, we return the potentially modified root node that now represents the pruned tree. This completes the Python implementation of binary tree pruning, where we ensure that only the nodes and subtrees containing at least one are preserved in the final tree structure. Here, we start with the definition of a binary tree node. The tree node class includes an integer value, and pointers to left and right child nodes. We also define three constructors: a default constructor, one that initializes the node with a value, and another that initializes the node with a value as well as its left and right children. Below this, we move to the main method, pruneTree. This method takes the root of the tree as input and immediately calls a helper function, contains 1, to check if the tree contains the value 1. If the tree does not contain any 1, the entire tree is pruned by returning null. However, if the root contains or leads to a subtree with 1, we simply return the root as is. The helper function, contains 1, is designed to check whether a given subtree contains the value 1. It starts with a base case: if the current node is null, it returns false, since null nodes cannot contain 1. Next, it recursively checks the left and right subtrees by calling itself on the left and right child nodes. If any subtree does not contain 1, that subtree is pruned by setting the corresponding child node to null. Finally, the function returns true if the current node's value is 1, or if either of the left or right subtrees contains 1. This recursive approach ensures that we only retain the necessary parts of the tree while pruning everything else effectively. Here, we begin with a binary tree that contains a mix of nodes with values 0 and 1. Starting at the root node, which has a value of 1, we recursively examine its left and right subtrees. First, we move to the left child, which has a value of 0, and evaluate its subtrees. The left and right children of this node both have values of 0 and no further descendants, so they do not contain the value 1. As a result, both subtrees are pruned, and this node itself is also pruned, returning false to indicate it does not contain a 1. Next, we move to the right child of the root, which has a value of 1. Since it has no children, it directly returns true, indicating it contains a 1. With this information, we see that the left subtree of the root is pruned while the right subtree remains intact. The root node itself contains a 1, so it is preserved in the final tree. Now, after processing the root node, the updated tree retains the root and its right child only. The left subtree has been completely pruned since it did not contain any 1s. Moving on to a new example, we consider a tree where all nodes have a value of 0. Starting at the root, we recursively call the contains 1 function on its left and right subtrees. As we navigate through the tree, we will determine whether any nodes or subtrees should be preserved. Let's break this process down step by step. For the left child of the root, which has a value of 0, we check its subtrees. Since it has no children, it immediately returns false, indicating it does not contain a 1. Similarly, the right child of the root, also with a value of 0, is evaluated in the same way. With no children, it returns false as well. At this point, both subtrees of the root return false, so they are pruned. Finally, the root itself, having a value of 0 and number 1s in its subtrees, is also pruned. The entire tree is removed, leaving us with none as the result. This demonstrates how the algorithm eliminates all 0 trees efficiently. In this new example, we look at a tree with deeper nesting. Starting at the root node with a value of 1, we evaluate its left and right subtrees recursively. The left child has a value of 0, and we proceed to check its subtrees. Its left child is null, so it returns false. However, its right child has a value of 1 and no further descendants, so it returns true. This means the left child of the root contains a 1 in its right subtree. We prune the left subtree and retain the right. Next, the right child of the root, which has a value of 0, is evaluated. With no children, it returns false and is pruned entirely. Returning to the root, we see that its left subtree contains a 1, while the right subtree does not. Since the root itself contains a 1, it remains in the final tree along with the preserved left subtree. From these examples, we can identify some key observations about the pruning process. A node is removed if neither it nor its subtrees contain a 1. This ensures that only the relevant parts of the tree are retained. The recursion operates in a bottom-up manner, beginning with the leaf nodes and working upwards through the tree. For null nodes, the base case immediately returns false, simplifying the pruning logic. This approach guarantees that the tree is pruned efficiently, removing unnecessary subtrees while preserving all nodes required to satisfy the problem's constraints. The time complexity of the pruneTree function is O(n), where n represents the total number of nodes in the binary tree. This is because the recursive helper function, contains one, is called exactly once for each node. At each node, the algorithm performs a constant amount of work. This includes checking if the node is null, evaluating the left and right subtrees, and determining whether to prune any child nodes. Since these tasks do not involve any additional iterations or loops, the time spent at each node is O(1). When we sum this up across all n nodes in the tree, we get an overall time complexity of O(n). Additionally, the pruning operations involved, such as setting node.left or node.right to none, are also constant time operations per node, meaning they do not add any extra overhead to the total complexity. Therefore, the time complexity is fully dominated by the recursive traversal of the tree, which remains O(n). The space complexity of the prune tree function is O(h), where h represents the height of the binary tree. This is because the algorithm uses recursion, and each recursive call consumes memory on the call stack. The depth of these recursive calls corresponds to the height of the tree. For example, in a balanced binary tree, the height is approximately log n, leading to a space complexity of O log n. However, in the worst-case scenario, where the tree is completely skewed, either left-heavy or right-heavy, the height could be equal to the total number of nodes, n. In that case, the space complexity would increase to O(n). Importantly, no additional data structures are utilized in this solution since the tree is modified in place. This ensures that the memory usage is limited to the recursive call stack, making the algorithm efficient in terms of space. Now let's analyze the best, average, and worst-case scenarios. In the best case, every node in the tree contains the value 1, meaning no pruning is necessary. Even in this scenario, the algorithm still visits each node once, so the time complexity remains O(n). The space complexity in this case is O(h), determined by the height of the tree. In an average case scenario, the tree contains a mix of zeros and ones. The pruning operations themselves are O(1) per node, so the time complexity still remains O(n), since all nodes are visited during traversal. The space complexity is again O(h), as the recursion depth depends on the tree height. The worst-case scenario occurs when the tree is completely skewed and contains a mix of zeros and ones. While the time complexity remains O(n), the space complexity reaches O(n), because the recursion depth in a skewed tree matches the total number of nodes. Comparing this to a brute force approach, which might involve multiple traversals and additional data structures, our optimized solution is clearly more efficient. The pruning is seamlessly combined with the recursive traversal, avoiding the need for extra memory or redundant passes over the tree. Finally, let's provide a mathematical justification for our big O analysis. For time complexity, we note that every node in the tree is visited exactly once, and the work done at each node is constant, or O(1). Summing this up across all n nodes, the total time complexity is O(n). For space complexity, the maximum memory usage occurs due to the recursive call stack. The depth of recursion corresponds to the height of the tree, h, leading to a space complexity of O(h). For balanced trees, where the height is proportional to log n, the space complexity becomes O log n. In worst-case scenarios, such as skewed trees, the height equals the total number of nodes, making the space complexity O(n). Overall, this solution is optimal, achieving O(n) time and O(h) space complexity, where h is the height of the tree. When solving the binary tree pruning problem, there are a few common mistakes that can trip up candidates. First, it's important to handle edge cases properly. For example, if the tree is empty, meaning the root is null, or if the tree has only a single node, some solutions fail to account for these scenarios, leading to runtime errors or incorrect results. Another common mistake is modifying the tree while traversing it without sufficient care. This is particularly tricky in recursive solutions where pruning nodes prematurely can cause references to parent or sibling nodes to be lost. Always process nodes in postorder, left child, right child, then the root, to avoid these issues. Additionally, watch out for inefficient subtree checks. A brute force approach that re-evaluates the same subtree multiple times can lead to redundant computations. Instead, use helper functions to calculate necessary properties, like whether a subtree contains a 1, and reuse those results. Lastly, don't assume all nodes will always hold valid values like 0 or 1. Some variations of the problem might use other values, so it's important to validate the node data and adapt your solution accordingly if needed. Overcomplicating the logic is another common pitfall. Many candidates write overly complex conditions for pruning or fail to leverage recursion effectively, resulting in solutions that are harder to follow and debug. Simplifying the logic and structuring your recursive calls clearly is often the best approach. Now, let's talk about how this problem often appears in interviews. First, recognize that this is a classic divide and conquer problem where the goal is to process children before evaluating the parent. Post-order traversal is critical here because it ensures that you only prune subtrees after fully determining whether they contain any 1s. To optimize your solution, let recursion do the heavy lifting by propagating information, such as whether a subtree contains a1, back up to the parent. During an interview, it's also essential to clearly communicate your traversal strategy and explain why post-order is necessary for this problem. Finally, a great way to showcase your understanding is to walk the interviewer through a small example tree, step by step, demonstrating how your approach works in detail. This problem also shares patterns with a few related problems that you might want to explore. For instance, LeetCode 112, path sum, involves traversing a binary tree to check if there's a path with a specific sum, which also relies on recursive logic. LeetCode 104, maximum depth of binary tree, uses recursion to calculate the depth of a tree, and LeetCode 543, diameter of binary tree, focuses on finding the longest path between two nodes. Practicing these problems can help reinforce similar tree traversal techniques. Now, moving beyond recursion, there are alternative approaches to consider. One option is an iterative approach using a stack. This avoids the risk of hitting stack overflow in deep trees, but it typically requires more code and careful tracking of state, such as whether a subtree contains one. Another approach is the mark-and-sweep strategy. Here, you first traverse the tree to mark nodes or subtrees that should be pruned, then perform a second pass to remove them. While this simplifies the pruning logic, it does require 2 full tree traversals instead of 1. Another less common approach is to use breadth-first search, or BFS, to prune the tree layer by layer. While BFS is not as intuitive or efficient as post-order DFS for this problem, it's an interesting alternative and worth experimenting with in practice. Each of these methods comes with its own trade-offs. Recursive solutions are usually more concise and easier to implement, but they can run into stack overflow issues when the tree is very deep. Iterative solutions, on the other hand, are more robust but result in more verbose code. Similarly, single-pass strategies like post-order traversal are faster and more efficient, but multi-pass approaches, such as mark-and-sweep, may be easier to reason about and implement for beginners. Understanding these trade-offs will help you choose the right approach based on the problem's constraints and your own coding style preferences. Great job! To wrap up, we explored the binary tree pruning problem, covering its key algorithm and takeaways. This problem emphasizes recursive traversal and condition-based pruning strategies. Thanks for tuning in, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!